Jack is a regional technical manager for ABB and the substation automation products supporting customers in Canada. He provides engineering, commissioning, and troubleshooting support to customers applying ABB's high voltage, protective, and automation devices. Prior to joining ABB, Jack worked as a substation P&C project engineer in 2 specialized consulting firms, and also as an engineering consultant to a public-owned utility in their transmission expansion and upgrade projects. Jack is a registered professional engineer in the province of Alberta, Canada. And now we'll bring the presentation over to Jack.
Thank you, Carrie. Good afternoon, everybody. Thank you for attending yet again this webinar on bus protection fundamentals. I have included my contact information, my email, and my phone number here. So in case you have any questions or for questions at the end of the session, time permitted, I am not able to answer properly or in completeness, feel free to contact me by email or by phone, and I will try to, we can have a thorough discussion on your questions. So the learning objective for today, in no particular order in later slides, is types of bus configuration, current transformer characteristic, and their effect, impact on bus protection, the different types of bus protection schemes, and some features in modern numerical digital bus protection relays. So why bus protection? So the bus faults usually are very robust, but it's also very rare. However, when it happens, chances are they are very severe. Okay, so seriously, things have seriously gone wrong. So also because of the different bus configuration available, under deployment, so different type of bus protection schemes are also available to counter and to protect different type of bus configuration. So in general, bus faults need to be cleared very quickly, especially for internal faults. And you need to, of course, stay stable for external faults. Lots of feeders, lots of lines tend to be connected to the buses. So if you misoperated on the protections, you might, inadvertently or unnecessarily take those loads off your system. Also, the delayed bus trip or mistrip could lead to network stability issues. For example, pole slip. If the bus fault need to be sub-cycled, especially for those high voltage buses near the generation plant, because a delayed tripping could cause pole slip or so-called auto step conditions that could destroy or damage the generators. Also, it could cause possible system collapse. Also, risk to human life. Okay, so bus fault protection is easy to detect because of the robust nature. Robust nature means typically the fault current is pretty high, so it's easy to detect. Okay, and easy to detect for internal fault. Typically, we use the differential principle. The summation of the currents is not equal to 0 for internal fault and has to be used and need to be near 0 for external fault. We use this principle to distinguish the fault is internal or external. However, the catch is that for external fault could cause current transformer saturation. Okay, and then that once the current transformer, which is your sensor, is saturated, it will not actually mirror or measure the fault current accurately, and that would also cause misoperation. Infrequent, the fault is infrequent, occurrence is infrequent, but it must be clear with high speed. For internal fault, it's stable for external fault, as I mentioned. So next, we're gonna look at some different type of bus configurations. So first is the single bus. Well, single bus is basically used typically for smaller stations. Okay, so sometimes you will see that still nowadays. And the next is the main and transfer buses. The advantage of using this type of bus configuration is that any of these breakers, the 4 breakers you see here, can be taken out of service, for maintenance, for repair, or whatnot. For example, you can, for example, from this 3rd breaker, you can open this to you can open the brake. You can close the tie first, and close the disconnect of these tie breakers, so that the tie breaker to supply the load of this feeder, and then now you can safely open the breakers and open the disconnect, so that you can put that breaker out of service. So this gives you that extra flexibility. Double bus single breaker, of course, this is very common nowadays. Typically we see a lot of this in the modern GIS switchgears. It's flexible. You can actually balance the load, freely balance the load, and transfer the load, between the two buses. The first bus on top and the second bus at the bottom. And then because of the two NOD disconnect here, you can actually connect the feeders freely to each of the buses. Follow the certain operation procedure, of course. However, and usually in this type of scheme, you have lots and lots of feeders, 20, 30 feeders connected to the two buses. But each feeder can be connected to either bus A, the main bus A, or bus B. However, the difficulty for protecting this type of bus configuration is that some type of dynamic zone switching must be in place. Because the feeder, the CTs here, this bus CT can belongs to either bus 1 or bus 2. So you need to be able to have a means to switch them. Depends on the location of this one of the two disconnect switches. For example, if this switch is closed, it's connected to bus A. If this switch is closed, it's bus B. So you need to have certain type of dynamic zone allocation scheme. Double bus, double breakers. This is probably one of the expensive type of bus configuration, because each of your lines, transformer, or loads are actually protected by two breakers. So of course you can take any of the two breaker out of service at any time and allow the other buses to feed the load. So it's very, very flexible and versatile and reliable, of course. Breaker and half, we see this probably the most often for high voltage or extra high voltage type of substation, especially for those transmission stations, on the switch yard of the big generation plant. So because they have three breakers and two feeders, so typically we call the breaker and half, because each feeder is actually protected by 1.5 breaker, 3 divided by 2. So again, this type of configuration also allow you to take any bus out of service for repair, for maintenance, while not disrupting the operation of the load. Ring bus. This is quite also typical in North America as well. However, the difference between this and the previous one is that sorry, I forgot to mention the previous one, that you can see these two dedicated bus bars for the breaker and half scheme. It will require its own dedicated bus protections. However, the buses that we call the bus stop here, they can be protected by the equipment protection. If it's a transformer, the transformer protection can take care and protect these small bus sections. For ring bus, basically they are same number of breaker as the number of feeders or loads. So, and also there's no dedicated bus bar. Actually, all these bus stops can be protected by the equipment protection. So it can be a transformer, reactor, or line. These bus sections, as you can see, are actually included in the equipment protection zone. And also, as you can see, all these bus stop protection zones are overlapped. This we call it simply main tie main. We see that a lot usually in distribution, medium voltage, level, and in industrial plants. So you have a tiebreaker. The tiebreaker can normally be operated as normally open or normally closed, and each of these two transformers should be rated to carry the full load of the bus. Okay. And you can have a dedicated bus protection to protect the main bus sections. Okay. So what are the issues about bus bar protection? First of all, you need to have enough CTs, and you need to have designated bus protection zones, and then you need to watch out for the so-called blind zone or end zone protection, which we will introduce a little bit later. And I have mentioned the critical in terms of some special bus configurations, such as the single bus, double bus, single breaker. The load or feeder can be switched. The CT can be switched to either bus. So you need to be able to switch the CT. Okay. And what happens when the current transformer is saturated or it's open circuited? How would the bus protection deal with it? So these are all issues that need to be addressed by bus protective relays. So first of all, most of you probably are very familiar with this type of schematics. This is protection zones. Just to highlight the green zones, the green color zones are bus zones, as you can see. Okay. So for zones of protections, here we just want to introduce the fundamentals of what they call for end zone or blind zones. Okay. So, excuse me. In a typical, for example, main time main scheme, if you consider this as a tiebreaker in the middle, typically in a switch period, you would order or specify CTs across the breaker like this, so they overlap to each other. The advantage of this is there will be no blind zone. Any fault here in the middle will cause the protection from the bus protection I'm talking about for the blue zone on the left and the green zone on the right to operate at the same time simultaneously. So there will be no, basically there will be no blind zone. However, when the breaker is already open, because sometimes, as I mentioned, this type of station, because the two transformers, the main transformer connected to it, for example, imagine the two transformers here, they usually are rated to carry the full load of the bus, right? So theoretically, and then normally the tiebreaker are operated as normally open, so you don't close this tiebreaker. So in that case, imagine if you have a fault hit here, okay, and obviously in this case, the blue zone, the blue relay, the blue bus relays will operate because it's the fault falls in his zones, right? And green zone will also operate as well, based on the contribution from the transformer, from whatever other sources there may be. However, the problem is, if the breaker is open, this blue zone doesn't really need to operate, correct? Because the breaker is open, there's no reason for this for this blue zone bus protection to operate, because actually you unnecessarily interrupt the service of the load on the left-hand side of this slide. So modern relay, for example, has a solution for that. For example, once you see this breaker is open, you can actually tell the relay. Of course, these type of algorithm has been designed in relay algorithm. So basically, once you see the breaker is open, you can remove the two CTs. So by removing those two CTs, for example, imagine if the breaker is operated normally open and you remove the CTs, these two CTs, then the blue zone will not operate anymore, but the green zone will still operate. So in that case, you will not actually, we call it overtrip. You will not unnecessarily overtrip for the blue zone relay. So similarly, for the other case, we have this type of situation. The same fault hit here, and you have a CT. And this CT now is not overlapping across the breaker. So your CT is here. As you can see, when the fault here, in this situation, the green zone, the protective relay, differential relay for the green zone actually will not operate because it is considered external fault to it. The blue zone will operate. However, if the breaker is closed, currently closed, and carrying load, the blue zone trip. However, the green zone will restrain, will not trip. So the fault is actually not clear because it's still being fed by the contribution on the right hand side from the green zone sources, green sources. So the solution again for that is once the breaker is open, you can remove the two CTs. Once you remove these two CTs, the connection, not the physical connection, but inside the relay, there's certain algorithm you can tell the relay to ignore these two CTs, the connection of these two CTs. As soon as the breaker is open, remove these two CTs, you can actually speed up the trip of this green zone relay, because once you remove this connection, the protection for the green zone will operate and clear this fault. Okay. And similarly, if this breaker is operate under normal open position, then you should remove these two CT sources to the protected relay. In that case, the blue zone will not operate at all. So again, you save the you prevent the over tripping of the blue zone relays. Okay. So talking about some current transformer, again, these are the fundamental some fundamental knowledge about current transformers. First of all, the modeling. The current transformer are modeled as a ideal current. So you would have a ratio current. So basically, it's the perfect replica of the primary current divided by the turn ratios of the transformer. Okay, looking at the B, and then you have your excitation branch, which can be represented by a reactance only. The resistance can be ignored, and then you have your lead, the CT lead or wires resistance, and your secondary CT winding resistance. Okay, and then you have your burden. The burden typically is your protective relay. Modern, low impedance protective relay, the burden is pretty low. So ratings for transformers, for current transformers, as we all know, there's different ratio for the current transformers. Okay, and then there are different accuracy class. So what do they mean? So the accuracy definition basically says for relay in CT, the NC and IEEE defines the limit of 10% for the ratio error. So it allows 10% error for a steady state symmetrical. What does symmetrical means? There's no DC offset. So it allows 10% ratio error for a 20 times secondary current at a standard rated burden. So in other words, so for the C800 CT, that tells us that this CT can withstand 800 volts on its burden, across its burden, its rated burden, with 20 times of the rated currents. For the 5 amp CT, that will be 100 amps without exceeding over a 10% errors of the measurement errors. Okay. The knee point saturation voltage are characteristics on the CT curve that you can actually derive from the chart in C-class CT. So what's the different type of CT classes? The C and K and the T. So the C-class CT is the standard CT with most of us come across daily. So those C-class CT means the flux is negligible. That they include the multi-ratio Bushin CT, window type CT, and then the CT excitation characteristic can be used to determine CT performance. So basically, the CT curve we normally see and what we have talked about normally for the transformer Bushin CT, breaker Bushin CT, or the standalone high voltage CT, those CT are all considered as C-class CT. And the K-class CT is similar to C. The difference between K and C is that the knee point voltage of the K-class CT is less than 0.7 or 70% of its rated voltage. Okay, so basically, for example, for the K200 indicated here, if it's considered a K-class of CT, then the knee point voltage must be greater than 140 volts. Basically, that's what it says. And for T-type CT, it means its performance cannot be derived, cannot be interpolated from the excitation curve. The manufacturer has to provide the exact curve of this type of transformers. Okay. And the last 2 points listed the relevant IEEE standard on CT, and most of you probably are very familiar already. So this is the CT performance curve that I talked about. Okay. So here, this is your knee point for this particular CT. It is the tangent, the tangent at 45 degree angle of the horizontal axis. So it's this point. And this 500 volt is your saturation voltage, okay, on the excitation curve. That is at 10% error, for 20 times radius circular curve. Okay, and then this Vx, obviously for C400 CT, this is 400 volts. So it's here. This is just to show you the different numbers we constantly talk about for CT and how they are related to each other. And then here give you, if you have this presentation will be recorded. You can see how you can estimate or specify a CT rating from the curve of the CTs. So again, this is I mentioned. So the definition of the CT class, this current transformer will deliver 800 volts for the C800 CT on the secondary when it's connected to standard burden and 20 times radial current flowing without exceeding 10% ratio. Okay, and these are the curves of the different standard burden corresponding to the different CT rating, voltage rating. So CT saturation. The CT core may reach saturation flux density due to a combination of DC offset. DC offset actually is the main causes of CT saturation, with possibly the resonant flux that's already contained in the CT that actually makes the CT more prone to saturation. So once the CT is saturated or slightly saturated or begin to saturate, the output current will suddenly change from a proportional signal to a reduction of that amount. And if it's completely saturated, you will be reduced to zero. So as you can imagine, if the secondary current becomes to zero because of the CT saturation, then your protective relay, doesn't matter what kind of protector, will not actually accurately measure any source of current from that current transformer. DC saturation depends heavily on the system time constant, X over R. This X over R, for example, is very large, and closer to the generator, for example. So that's why for the generator differential, you have when you are designing the generator, when you are calculating the setting for the generator protection differential relay, you need to be watch out for this X over R impact on the CT saturation, because you will see a very big value, big number of this X over R. So when you specify a CT for a generator protection purpose, then you need to watch out for that. Okay. Again, we talked about most of this. We need to emphasize on the parameters called time to saturation. So the importance of time saturation is when you specify a CT properly, okay, every CT would saturate. But if you specify a CT properly, according to the load, according to the short circuit level, according to the X over R ratio, for example, like we mentioned before, then this CT shouldn't saturate right away. It should at least give you a couple milliseconds or even a cycle time for the relay to properly measure an accurate replica of the primary current in order for the relay algorithm, differential algorithm, to operate. If the CT saturates right away, let's say, if the CT wasn't sized or specified properly, it would saturate right away, and in that case, chances of misoperation could happen, and then it could create disastrous consequence in terms of bus protection. So the bottom line is the CT need to be properly sized and specified so that you give a couple milliseconds even, because modern relays can handle up to even 2 milliseconds, 3 milliseconds of healthy secondary CT current waveform, so that the relay can make the correct decision to trip or not to trip. Okay, some issues affecting bus protection selection. For bus arrangement, fixed or switchable, that's what we mentioned before. Availability and characteristic of current transformer, that we cover, and some performance requirements, speed, dependability, security. So in general, bus protection need to operate fast for internal fault and need to be absolutely secure for external fault. So different type of bus protection system will be introduced later. First of all is the differential. Most bus protection scheme we have seen nowadays are all differential. So starting with the most simple differential connected type of overcurrent to the legacy percentage restraint differential to the still very commonplace high impedance differential, partial differential, and also the numerical differential relays that we have come to see very widely, very common nowadays. And then we will introduce the zone interlock scheme and some backup schemes. So what is the differentially connected overcurrent relay? So it's very simple. It's the overcurrent relay, 50 or 51, depends. That basically you sum the CT externally and bring the sum, so externally through hot wiring, and bring that wire into the relay. That's all. So basically it's overcurrent relay. So but because you externally sum all the CT, so it behaves as a differential relay. However, the disadvantage of this type of scheme is that first of all, because this relay has no internal algorithm to deal with any type of CT inaccuracies or measurement errors, because remember, there will be 10% error. The CT rating NC class, C class allows up to 10% of measurement error. So those measurement errors will become a false differential current for the bus differential relay. For your differential relay, in this case, is this overcurrent relay. So depends on. So the worst case could be 20%. If the 10% error is in one polarity, the other 10% is the other polarity. So when they subtract, they kind of add together. That becomes 20%. So when you enter or calculate the pickup current for this relay, you need to be very careful. You need to, of course, the pickup relay need to be higher than the potential false differential current in order not to misoperate. And also, the major drawback of this type of connection is, obviously, there's no internal algorithm, as I mentioned. So there's no way this relay can deal with, for example, CT saturation. So modern bus differential protected relay can all have certain type of saturation detection algorithm, or have dual slope, or sometimes some have triple slope to deal with CT saturation. But this simple type of connection like this wouldn't have that type of arsenal in place to deal with that type of complexity. Okay, so basically the next two slides basically shows for external fault, when the CT saturates, you will have the excitation current flowing through the excitation branch, and that very current, assuming the other CT are well behaved, then that current will become your false differential current, and your pickup need to be higher than that, or otherwise your overcurrent relay will misoperate. Internal fault then basically is the summation of currents that we all know. So the conclusion for this type of simple design, the prerequisite for using this is you are very confident, you are very sure that you have sized and specified your CT based on the current alone, and you are pretty sure that, and based on the current, based on the fault level alone, and you are pretty sure there will be no chance of CT saturation in this case, because the relay is not capable of dealing with CT saturation. Okay. And as you can see, that's the reason, because you need to set up the pickup quite high to override, to write through the the measurement error. So that's why it's not going to be very sensitive. Okay, so the typical pickup is greater than 10A secondary, 10M secondary. Next, we're gonna introduce the principle of restraint. We heard restraint a lot nowadays in modern, differential relays. They are all digitally designed, but the legacy type of restraint relay are basically restraint windings, as we can see here. I can't say too much. I can't discuss too much, but the idea is when the current passes through the restraint winding, if the winding has the same directions, okay, if the current passing through the winding in the same directions, the net restraint is 0. Okay, so basically they are subtractive. If the currents pass through the winding in different directions, as in this case, then their resulting restraint effect is additive, okay, additive. So in this case, for the external faults, you can see you have the high restraint current. Next slide shows you that for the same type of bus configuration, same type of relay wiring, you can see that for internal faults, since all the current going through the same direction through the operate coil, you can see that there's no restraint, and that the operate current is higher than the restraint. And how do we use this restraint? For example, in the previous external fault case, then the relay manufacturer will issue a plot, a graph, a design. That's how they design their relay. It's all about torque. If your operating torque is higher than your restraint torque, the relay operates. If your restraint torque is higher than the operating torque, the relay restrains. So that's why, as you can see here, for the 60 amp restraint, for example, and depends on if you have a 1 restraint or 2 restraint or 3 restraint, you will require different amount of operating torque in order to operate. So in other words, if you have a restraint winding in place in your relay, then it will accumulate the restraint torque. So that will end up overcome your operating torque. So that makes it more secure for external fault. Okay, as we know here, for internal fault, it's actually 0 restraint. It's designed that way so that you will operate at ease. Okay. So here, it actually just talking about the same thing. For the 50 amp of restraint, overcome 7 amp of operating current. So basically, if you have somehow during the external fault, CT saturation or something caused a 7 amp of operating current, as long as you have at least 55 amp of restraint current, then you would overcome that, so you won't misoperate. So the advantage or conclusions of multi-restraint percentage differential type of relay is that good sensitivity, good security, allow other CD on the same CD core. Basically, this is the characteristic of all modern low impedance type of relays. Different CD ratio with auxiliary CT. The legacy type of relay all require auxiliary CT to match the CT ratio. It's relatively slower than high impedance relay, but number of feeders but the number of feeders is limited by the restraint winding. As you can see, each feeder, each connected CT need to have its own restraint coil. Each CT is wired to the relay, so that also means it's not easily extendable because the number of feeders is limited by the number of the restraint winding. So next, let's introduce the high impedance type of bus protection. We still see this a lot because this this type of protection scheme for bus is quite simple, easy to apply, and quite secure actually. And the performance, the speed is also very satisfactory and very fast. How it works is, remember before, for the very simple overcurrent type of relay connected in a differential way with all the CT connected in parallel and bringing to the relay core. Imagine that the high impedance relay is nothing but this exactly same type of wiring, but put a extra big resistor over, in this case, over 1500 ohms, basically very high resistive, very big resistor in series with your operating coil, relay coil. So why? So let's go back here. Okay, the reason is that, so here is actually dissections of this type of high impedance relay wiring. As you can see, for high impedance relay, you put a big resistor basically in series with your operating coil, and you put the MOV. MOV is a device that will short after the voltage reaches a certain level. The reason is to protect the insulations, insulation of the cable of the wiring, because you don't want to have too high the voltage suppressed on all those cable insulation for too long a time, basically. So you want to have MOV here. Actually, some vendors suggest using the 86 lockout relay in parallel as well. So that means as soon as the relay operates, that lockout relay contact will close and short out the high voltage branches. So basically, they will short out the high voltage to reduce the over voltage, kind of keep it to the minimum amount, and basically reset it as soon as the relay operates. Okay, so this is the way a dissection, a view of how this type of relay configuration connection can be analyzed. You can see here on the left-hand side there are multiple CTs. Okay, there are multiple CT connected in parallel. On the right-hand side is one CT, so we call it CTA and CTB. In fact, the CTA are a group of CT connected in parallel. So we are talking about, and you can see the polarity of these two perfect current sources that represent the CTs. You can see that they are in actually the same direction. That would mean we are talking about indicating the external flow. So during the external flow, the current flows this way. So what happened is when you have a big resistor here, okay, so you have all your CT contributing current into the circuit. However, because normally you would, because of the external flow, let's imagine for this CT saturated, completely saturated. That's how we usually estimate the settings for the high impedance bus protection. If we have if you have a CT completely saturated here, normally we wouldn't have any currents here, because all the currents from CTB will go through the excitation branch, and that will cause misoperation. However, the high impedance relay, the way how it works is this resistance, because it's big, it will force the same current here to that branch. Okay, so the current through this branch, okay, will actually create voltage drop across these two resistors. These are the CT lead resistors and also the CT winding resistance. So the voltage developed here actually is also actually because for the completely saturated CT, this is basically the short circuit. So really across this branch, okay, really this branch will actually feel the voltage of this current plus this current flowing through the RL and RCT, the two resistors. So that's why you can see to calculate the operating setting is really this type of relay is really become a voltage relay, over voltage relay. So you have your setting calculated as the current, okay, your full current divided by your CT ratio, that's your secondary current, multiplied by the resistance, total resistance of the CT lead and also the winding. So, and then you will add the margin. And rest assured that through the calculation like this, this will be the maximum voltage that this circuit can ever experience during a fault, during an external fault. So only internal fault could create voltage higher than this. So it's very secure because we know that during external fault, no matter how badly the CT saturated, because we already assume the worst scenario, no voltage can be higher than this, plus margin. Okay. So this is to calculate the setting, the minimum operating settings. We also need to assure the sensitivity of this relay. Because there are so many CT, this is, as I mentioned, this is a group of CT, and the current must also charge the excitation branch. You also need to flow through the resistor, flow through the NOV. So you need to have the sum of all these together to estimate what is the minimum required current for this operating voltage VR, that the current that's required in order for this skin to operate. So in other words, your fault current need to be higher than this. So that determines your sensitivity. Okay? So this is a very quick and easy introduction of high impedance bus protection. So some criteria need to be met for high impedance bus protection. As I mentioned, we actually try, we don't want such a, of course, when we calculate the voltage here, we can calculate according to the, you know, the application, the guide that I just mentioned, you know, based on the resistor here. So what if you have a very big resistor? This RL, again, remember, this is the CT lead. CT lead means the resistance of the CT wires from the CT terminal junction box back all the way to the relay root. These are your lead resistance. So if you have if you have a huge resistance here, obviously you will get the base. If you have a current flow, because that's your the short circuit current is a product of your system design, is your power system. So you cannot change it. So and this winding resistance of the CT, again, you cannot change it. That comes with the manufacturer. When you buy this CT, specify this CT, you stuck with it. So you cannot change it. But what you can change is this RL. If you reduce the size of this RL, you can effectively reduce your VR. So basically, the relay does not need to operate with such a high voltage, because high voltage is actually detrimental to your cable insulations, right? You don't want to constantly hit it with high voltage. So how to reduce it? You know, obviously, as I mentioned, reduce the RL. How to reduce it? You can try to keep the CT secondary loop resistance low. How to do that? Impedance from junction point to the relay, that is of no consequence. So what it's saying is, this portion, because of the huge resistance here, this portion, doesn't matter how long, how big this portion is, so this portion represents the junction point to the relay terminal. So that is, if you can try to parallel your CTs outside the yard, near the CT, near the physical CT junction box, for example, then you can reduce the RL because the length, the resistance between the junction point to the relay terminal actually is negligible because of this huge resistance, 1500 ohm resistance here. Okay. And theoretically, there's no limitation in the number of parallel CTs, but remember, we need to calculate the sensitivity of this scheme. The fault current need to be higher than the minimum sensitivity, current sensitivity of this scheme in order for the relay to operate. So if the more relay you added in parallel, the higher the I mean would be. So in that case, you make it less sensitive. Okay, so that's actually a judgment call. But theoretically, there's no limitation. You can actually keep paralleling your CT together if you like. This is from a paper I read many years ago. It's a very good paper from WPRC. If you set VR, which is your protection settings here, higher than the CT rated voltage for example, the 400 volt for the C400 CT, 800 volt for 800 CT, which will produce error when estimating CT exciting branch current. That is, when you are actually calculating the exciting currents here, you usually estimate via using the CT excitation curve that I showed you earlier. Because the reason is that because for voltage higher than the rated voltage here, the excitation curve, the CT has already entered or is beginning to enter saturation. So the excitation current is not linear anymore. So it's really hard. A small increase in voltage will increase that excitation current in a big margin. So that would not be accurate anymore to kind of derive that exciting current from the curve. So that's why there will be errors when you estimating the sensitivity of the CT. Okay, and one disadvantage of the high impedance based bus protection is that all CTs must have the same ratio and magnetizing characteristics. Unfortunately, there's no other way around. All CTs must match. Okay, so next we're talking about differential comparators. These are the type of differential algorithms that we all have come to know in the last 20 years. And what I have shown here, these are the legacy type of relay in ABB, IEDSS. Some of you might be familiar with it because this is a very good relay that was developed in the 1980s. You know, I've still seen a lot in utilities nowadays. Of course, they have reached their end of life. So the idea is these are static relays. So basically, it measures the in current and out current. What is the in current? The definition of in current is all the current. So they actually group the relay algorithm, group the current divide the current into separate groups. The current in the same direction belong to one group. The current going to the other direction belong to the other group. And compare the two, which one is larger? If the sum of the current going in one direction is larger than the other group, then that is called the in current. Okay, so it's basically the sum of a group of current going in the same direction. Okay, so in and out. So the larger group is called in, and the smaller group is called out. Okay, so basically, so like imagine if you have external faults and all the current going through the same direction, but one CT current, because that's the current that's the CT that all the current is taking the exit off. So that current will be the out, and the other one will be the in. Okay, and the differential obviously is the in minus out. Okay, it's a sum of the two, a vectorial sum of the two. I'm not going to touch too much about this. This basically is the old way of implementing this type of protection. So it's based on diodes and based on resistors, all static devices to develop the voltage and torque in order to operate the relay. So I actually have not really have the first-hand experience working with these relays, so I'm not going to go into too much detail, but the idea is quite simple. Typically, the differential current is typically small for external fault, and restraint voltage is greater than operating voltage. Okay, and for internal fault, the differential current is typically very large, of course, and the operating voltage is made greater than the restraint voltage. So this is very similar to the low impedance restraint type of differential relay that we covered earlier. So basically, you have two torques, operating torque, restraint torque, and see which one is bigger, and it will override the other. Next, we're going over the numerical differential comparators. So the same type of relay, same type of principles. You compare the current contributed into the device. You compare them and make decision whether it is an internal fault or external fault. The previous devices used the static diode, static components. modern relay use numerical calculations to actually estimate, to calculate the differential current and compare with the set slope and pick up settings to decide whether to operate or not. So analog input currents are instantaneously sampled and quantized to numerical number. As we know, these are the same for all typical relay. And from these digital values, you will estimate the phasor, calculate the phasor associated to each instantaneous current value. And then the phasor, the fundamental 60 Hz phasor value, are fed to the differential functions to calculate the differential current, the restraint current, and then compare them against the slope, the set slope, and to determine whether to operate or not. So it's a similar technique to legacy differential comparator, but with measured sample data. Secondary circuit loop intensity is no longer a critical factor. Critical factor is the time available to make the measurement, or AKA time to saturation. For example, in ABB relay, only 3 milliseconds is required to properly restrain for heavy external fault that cause heavy CT saturation. So more or less, every vendors will have the same type of CT saturation detector, and to help stabilize for heavy external fault. So again, the same idea. Differential is based on input minus output, but the difference is this time they are actually numerically calculated, those current values. And then there's a set percentage based on settings. So you will see this familiar slope here, and then the operating region is above the slope, restraint region is below the slope. Okay. So what are the advantages? For modern differential comparator, obviously lower CT requirement. The CT doesn't need to match to each other anymore. Usually, it can tolerate 10-to-1 ratio differences in the same, parallel differential circuit. It can allow much higher CT loop resistances. The reason is because the burden of the relay is very low nowadays. Accommodate different CT ratios, auxiliary CT, no auxiliary CTs are needed actually right now, and fast operating times for internal fault. And it will detect internal fault in 1 to 3 milliseconds as long as you provide a free, unpolluted CT secondary for that amount of time. So some graphical explanation of how modern relay operate for internal fault or external fault. So in this case, as you can see, we have instantaneous values signified by the green, for the blue and the pink. Okay, so these are instantaneous values. Those are your sinusoidal waveform, if you like. And you can see you have a standard load current here flowing. All of a sudden, the fault hits. Okay, so so this is internal fault. So during internal fault, all the current going into the same direction. So really, all the currents are your incoming current. Let's call it that way. So your incoming current rise and your outgoing current drop. And then the yellow and the light blue depicts the phasor, fundamental 60 Hz phasor RMS values, for example. So you can see, and then the phasor value are what the relay operates on. So you can see as soon as the differential current goes above the operation level, trip is issued. Okay. So this is how the relay operates during internal fault. And next, let's look at how the relay operates for external fault. Again, during external fault at the beginning, everything is stable. You have normal low flow. Okay, everybody's happy. But as soon as the fault happens outside of the protection zone of the bus protected relay, you can see at the very beginning, so this is critical, the relay need to have this amount, the minimum amount of time to see that a fault happened. And actually, when the fault happened, internal and external fault rise at the same time together as before. So they rise at the same time. But after, let's say, 10 milliseconds, the CT start to saturate, and they start to pull apart, as you can see here. Okay, similarly, you can see the instantaneous value. They start to pull apart. They stop coinciding with each other. And then this is when the relay knows that this is an external fault. It's not an internal fault, it's external fault. Even though the differential current here is above the pickup, but it will extrain because the relay will look at this, detect that in and out at the beginning of the external fault, but it knows that it rise together, so they conclude that this is an external fault. Even though there's a differential current, significant amount of differential current, it will securely restrain. So this is basically also part of the CT saturation detection algorithm. That's how they look at it. More or less, every vendor has a different way, but all of us looking the same thing. They analyze the waveform. In addition to that, what if the CT actually has an open circuit or short circuit? So basically, it doesn't pass the current, to the relay anymore. So you can see how the relay analyze this or prevents from operating correctly. So at the beginning, you will see that the current coincides during the normal load, but just after a certain time, the relay concludes that there is a normal load situation, but all of a sudden you have a drop in the outgoing current. You can see here the incoming current stays the same because there's no fault, but there's a drop in the output current, so for no reason. So that actually the relay will conclude that this is an open CT situation. So it depends on the settings. In our relay, we have different, settings that you can set to tell the relay what to do, either to block or to alarm or to trip, or it depends. Because open CT could cause overvoltage problem. It's a risk to field crew. So sometimes you would like to trip. So here is some explanations here. The detects that the input and doesn't change while output goes down. Okay, so you determine that it's an open CT or short circuit CT. If the differential current, resulting differential current is higher than the setting or open CT level, the IEV is blocked or determine whatever setting that you instruct the relay to do. Okay, other features in modern numerical bus IEDs. So in modern numerical bus relays, actually, each device is nowadays capable of connecting multiple bays. Just like the high impedance, relays. Actually, nowadays, each box protection relay, we call it a box. Some of them, most of them support at least 6. You can connect to 6 3-phase CT to it. Some can create 8 connected to 8 CT and protect those 8 bays. Or you can opt for the single phase design. Single phase design means 3 phases, because bus differential protections are phase segregated. Each phase make independent decisions, so it doesn't matter they are located in the same box or separate boxes. So for single phase design, obviously you will have 3 boxes, each making their own decision, but the advantage of that is then you increase. For example, if you can connect 8 3-phase CTs in one box, you have that capability in your analog input I/O modules. Then that means for a single-phase design, you can actually connect 24 single-phase CT because 8 times 3, right? 3 phases. So in other words, you can protect 24 feeders, with 3 boxes in this type of low impedance system. Okay. And then modern numerical bus IED all should be equipped with these type of functions. We talked a little bit about it before. Multiple differential zones, so you can actually freely divide, the bus differential into different zones, so they operate separately. You can assign different CT to different zones, for example. Dynamic base switching. The CT need to be able to switch to which zone, or depends on the status of the switch or status of the breaker or whatever logic you create. So basically, you need to be able to dynamically switch the CT. Zone interconnection. Sometimes, for example, for the double bus single breaker scheme, if you close the tiebreaker or close any of the two breaker disconnect switches at the same time, you effectively are actually interconnect the two buses. So in that case, you want to make sure now all the CT are actually connected to the same zone. So you need to have the different logic for zone interconnection. And also check zone. Check zone is to make sure you can further supervise the security of your bus bar protection by using the check zone to supervise the operation of the differential protection. And we talked about the external fault or CT saturation detection through the graphical representation. Blind zone, end zone, we'll talk about it in the next two slides. Backup protection, modern numerical bus relays all should be equipped with bus backup protection such as overcurrent, one for each feeder, breaker fail protection, one for each feeder. Especially breaker fail protection really comes very handy, because think about it, for those type of double bus bar single breaker scheme, any CT, any breaker can be connected to either buses. How would you know which bus this breaker is currently connected to? If you use a separated breaker fail individual or standalone breaker fail protection relay for each breaker, then you may run into trouble. You need to kind of create some customized, very heavy customized convoluted logic to determine exactly which buses this very breaker is currently connected to. But if you use the breaker fail protection inside the bus protective IED, then that information is already known and available, and it's calculated it's processed by the bus protection algorithm because of the disconnect switch that you provided to switch the CT to the different buses. So those information is known. So when the breaker fail happens, it will operate and trip the right buses, trip the breaker, only the breaker connected to that bus, and not going to trip the other breaker. So this is very important and handy function in modern numerical relays. And next but not the least is the modern substation automation communication. DNP3, 61850, as we all probably have heard. These are actually probably the requirements in modern, if we call the relays an IED, intelligent electronic device. They need to be equipped with communication, automation, communication capabilities. Okay, blind zone detections. We talked about this a little bit. So basically, we have if we have only have the single CT not overlapping with each other. Okay, if the tiebreaker is operated normally closed, zone A will operate because of the CTs. Okay, if the fault strike here, but zone B will restrain. Okay, because that's outside the zone. If the tiebreaker is normally open, again, zone A will operate, but the fault is still there, it's not clear, but zone B will restrain. So the solution, however, solution then we mentioned before is to connect the status or any type of logic to indicate that, hey, the breaker is open now, so remove those two CTs from the differential zone, operating zone algorithm, differential calculation, so that once you remove that CT, zone B will operate, okay, and zone A will restrain. So that you will not cause unnecessary operation in zone A and can speed up operation of zone B. A different look, different scenario like this. Of course, this is for illustration of the principle purposes only. So it doesn't really happen this way because when you design the station, you would definitely align the CT on the same location. If you would put the CT on the north side of the breaker, then you would put CT on across in the same way across all breakers. You wouldn't put two CT this way and the other two that way. This is just for illustration to demonstrate the concept of the over tripping and under tripping, right? So for the fault strike here, as you can see, by the way, this type of design is very common for high voltage, breaker and half stations, right? So this is your dedicated bus, for example, and this is your one of the bus breakers, for example. And when the fault is strike here, the measuring CTs, when the fault is strike here, the bus will operate. Okay, the bus definitely will operate. However, the fault is not clear, right? Because the contribution, the source from this side will still continue energizing the fault curve. So in this case, what you can do is once the breaker is open, to avoid over tripping on open positions, you can set up a fast overcurrent relay, say instantaneous overcurrent relay. That is enabled when the breaker is open. In that case, when it detects still current flow, it will send a direct transfer trip or any type of communication assisted tripping to open the breaker at a remote end. In that case, you can completely isolate the fault. Okay. For 4, if you have a fault here, for example, okay, and the breaker will open, okay, because of the feeder protection or any other type of protection here, but the fault will still be energized through the buses, right? Because the bus is external to the bus. So again, when the breaker is open, the idea is still the same. You remove the CD connection internal inside the relay, then the bus protection will operate, okay, safely and quickly once the breaker is open. There will be a slight delay, but in this case, at least you don't have to wait for example, the breaker fail protection or any other backup protection, usually with time delay of 10 cycles or more to save the day. If you use this way, you can actually clear the fault on its own quickly. So other type of bus protection method, partial differential or blocking or feeder current. So what is partial differential? Partial differential usually means you actually group the sources typically together. Okay, so I guess this arrow was drawn incorrectly. So these are sources, these are the load. So you usually group the sources together and connect it to the overcurrent. The reason that you do that is then these 3 sources becomes one. So when you need to coordinate the overcurrent protection between the sources and the fuse, for example, or any feeder overcurrent relays there downstream, you don't need to coordinate or draw 3 times the curve, because right now since you sum them externally together, it only becomes one relay. So that actually reduces the amount of work and make it easier. Okay. Okay. So next, blocking scheme. So this type of blocking scheme requires certain type of communication. So the idea is sometimes it is economically not justified or not necessary to put a bus bar protection, dedicated bus protection here. So how are you going to protect the bus, right? You have the main incomer relay, you have a feeder relay. So the only way is for the two group of relays to communicate with each other. In traditionally, you use wires. So whenever a fault happens, so that's why we call it blocking scheme. Whenever the fault happens on the feeder sensed by any of these devices, you will actually close the output and then send a signal to the input of the main incoming relay. So that to block the operations. So if the fault is on the bus, and assuming there's no backfeed from the feeders, then these 50 relay will not sense or detect the current. So you will not actually signal actually will not send any blocking signal to the main incomer relay. In that case, the incomer can trip with a certain time delay for safety margins. So here's the scheme and also a tabulation of the time delay required. So as you can see, traditional busbar protection based on upstream blocking. Dedicated hardwire signal path is needed from the output of the feeder back to the input of the main incomer. So signal path delay needs to be considered. Input and output relay plus auxiliary relay. Changes in the protection scheme may require rewiring. So basically, you need to wire, but that's how it was done anyway before, with lots of wires between the relays. So the estimated typical needed delay in the incoming relay is over 100 milliseconds. Okay, so but again, that's better than nothing, right? You have a bus fault. If you don't use this type of blocking scheme, these main incoming overcurrent relay need to be time coordinated with all the feeder relay, and that definitely will be more than 100 milliseconds. So this can save you time to operate for the true bus fault for within 100 milliseconds, which is very useful, which actually speeds up quite a bit. Now, with modern substation automation communication technology in place, such as 61850 Goose, peer-to-peer event, publishing event. So now it has been estimated that the time delay mentioned here can be cut and reduced significantly. So altogether, it can save about 50 milliseconds of delay time based on the relay-to-relay communication. And also, in addition to that, obviously, you would get rid of tons of inter-panel, inter-relay wiring, termination work, labor, everything of that can be saved through this type of peer-to-peer communication scheme. Next, but not the last, is the comparison chart that illustrates the different type of bus protection scheme that I have covered in this presentation in terms of cost, ease of use, sensitivity, dependability, security, flexibility, and speed. You can look into this in more detail if you like, but in general, modern bus protection type of relay approach have all basically migrated to more low impedance type of approach because the less rigorous requirements on CT requirements, and also because that's the trend for modern numerical relay development and technology. Okay. So here, if you have any questions, I will take a look of the question list. But here is the NC IEEE guide. If you are interested, you can take a look. Also, PSRC has some very useful supplementary tutorials on bus protection. You're welcome to take a peek there too. So thank you for participation. So for information, questions, you can actually email me as I provided earlier at the beginning of the presentation. And then you can also subscribe to our YouTube channel, to view the recorded webinars and other technical with respect to our ABB most related products. So, how much time do we have? 15 minutes. Okay, let me see if there's any questions. There's lots of questions, but I do not know. How do I enlarge this?
Jack, you need to click the undock pane. The little next to the X is undock, and you can make it bigger.
Yeah.
Can you see it now?
Yeah, but can I just make it bigger for the questions, or is the whole thing?
I think that's as big as it goes.
Okay, I see. Okay, let me see. Okay, I have to go back to the top. Okay. Can we have a copy of this? First question, can we have a copy of this presentation? I think
it's already attached, Jack.
Okay, all right.
Yeah, it's attached, and also the certificate of attendance is attached as well. So if everyone wants to grab those before the webinar is over, if you don't get a chance, you can always send me an email, but go ahead and grab those now if you can.
So most people asking the same question. What makes the high impedance differential relay in 87 type versus 5051 type? Well, that's a good question. Actually, I don't think it's the 5051 type. I don't even think that's the 87. The reason it's the 87 type is because of the wiring connection. You actually, 87 differential means you basically connect all the CTs in parallel, right? That's differential, the nature of differential connection. So really, in my opinion, the high impedance type of protection is really a over voltage type of connection. It operates based on voltage, not really current anymore. So in my opinion, it's neither differential. It's a differential in terms of connection, but its operating principle is not actually 50 nor 51. Okay, but you do have to make sure you calculate the sensitivity based on current. So you need to make sure your overall fault current contribution for internal fault is higher than that minimum threshold in order for the relay to operate. Hope this answers your questions. What are the impact of the lead length on the high impedance protection, and how can be compensated? Like that I mentioned earlier during that couple slides about high impedance relay. The idea is you really because the standard wiring for example, these are for CT wirings, right? So it's 10 AWG 10 gauge wiring, sometimes 8 maybe. So they are a standard voltage rating to ground, right? You don't want to extend that. So I'm not 100% sure. Don't quote me on that, but I remember it's about, let's say, 1,000 volts, right? So you don't want to suppress over 1,000 volt of voltage, or even close to that, for that matter, to your CT wiring, right? So basically, in other words, when the relay operates, you don't want that VR to be significantly close to your wire CT lead rating, whatever rating that is. So you want to keep that as low as possible, basically. So in order to keep that low, like I said, you cannot change the CT winding resistance, because that's how the CT is. That's the components of the CT, unless you kind of specify that or during the procurement of your CT. But sometimes when the CT could be purchased 30 years ago, it's hard to say, right? So you don't know. You have no control for that. So so really the only way you have under your control is to reduce the length of your CT cable or wires, whatever you want to call it. So how to reduce that? As I mentioned, if you try to parallel your CT as close to the CT junction box in the yard as possible, as much as possible. Sometimes maybe depends on company policy. Sometimes it's not applicable, right? I mean, you can't put. I mean, it depends. Like if you can parallel or sum your CT near the CT junction box in the yard and bring that single wire into the relay, then that would significantly reduce the amount of lead, equivalent or effective RL, the CTZ resistance, because only the length between the CT secondary terminal to the junction point counts as RL. Okay, so if you can parallel as close to the yard as possible, you put the marshalling panel there or whatnot, you can reduce that resistance, and that will effectively reduce your VR setting. Okay. Next, is there a next? Would this presentation, okay. Could you please repeat the idea of preventing over-tripping with removal of CT when the breaker is open? What does it mean? Okay, so when I guess I did not use the right wording when I explained about removing to prevent under tripping by removing the CT. I'm not talking about physically lift the wires on the terminal. That's not what I meant, because you wouldn't be able to do that. The wires, the CT wires, will be connected to the relay as is, but modern numerical features, numerical relays, there has to be a feature allow you to tell the differential protection that this CT now is contributing 0 current. Effectively, that means you disconnect it. Okay. So basically, if you can provide create a logic by connecting a breaker status or some sort of status in there, creating a logic saying if this is true, my contribution from this CT is 0 to my protection zone. So in that sense, you are removing the contribution of that CT current to the to your bus protection. But what I didn't mean to physically lift the CT wire. That's not what I meant. Sorry for the confusion. This is really, what is the typical fault clear? What is the typical fault clearing? Is this the one? Okay, I think so. So what is the typical fault clearing time required in the design of bus protections? This really depends on your systems. Typically system you need to, so like the planning department usually have software like PSCAD or ENTP-based software to calculate, the transient, to perform conduct some transient studies, and to understand that. So what is the critical clearing time for a 3-phase fault, for a single-phase fault that is required, so that not to jeopardize the transient stability of your system, for example. Especially faster clearance times needed closer to the generating plant, such as those switching plant right outside the big generators. So for example, like typical, there's a project I was involved earlier a few years ago, like you need to speed up the protections by, for example, the critical clearing time is 5 cycles, for example, including breakers. So that's why they need to upgrade the breaker to modern with like 3-cycle breaker, and then you need to make sure your protection is sub-cycle, which means under 17 milliseconds. So but that depends on the system, and depends on the location of the fault of the bus as well. In the comparison slide for various bus diff skin, it was mentioned that sensitivity of blocking skin is poor. If an element in modern numerical IED is specifically allocated use for this skin, can this protection be set very sensitively? Well, the reason that it's poor is you wouldn't, in my experience, you wouldn't allow that bus protections to, how should I say, because that bus protection 51 relays, if we go back, still have time, a couple of minutes. Okay, I want to. But anyway, I just want to go back to show it, but somehow I can't. Anyway, I try to explain the best I can. I mean, even though you can speed up the protection for fault on that medium voltage bus with this reverse blocking scheme, yes. The advantage of that is that you actually can reduce coordination margin between your incoming overcurrent relay with the feeder relay. Otherwise, you have to at least maintain 0.3 seconds, which is 300 milliseconds of margin, sometimes more, depends how many devices in the middle. So you will wait a long time. And because of that, your sensitivity suffers, right? You are actually drifted, your curve, protection curve is drifted to the right, right? But because of reverse blocking, you can actually reduce the margin, but not so completely that you can actually you definitely cannot allow that protection to operate before the feeder. And most, you can allow the shorter margin, let's say, 100 milliseconds or something. So you still need certain type of coordination time between the feeder and the main incomer, but the margin can be reduced and more, and the requirement is more lenient. That's my understanding. Okay. Yeah. Okay. I think that's all the questions. So there's a lot of question requests regarding the copies of this presentation. This presentation will be recorded anyway, so you can actually go to YouTube and listen to it if you like. So yeah, thank you for attending. Let me know if you have any questions. Thank you.
Thanks, Jack.